Hello everyone, it's good evening. Today's topic that welcome to your class, and I got the chapter that is your mathematics for chemistry as well as mathematics for biology. Biology for chemistry. Both the topics are there. Mathematics for chemistry as well as biology for chemistry. So thing is that we have to understand that why the math what is the link of this mathematics and biology in the subject of the chemistry. So today our topic is mathematics for chemistry, and 21st and 22nd, that days I'll complete your syllabus mathematics for chemistry. And in this connection we have to understand what is exactly why you are studying mathematics in chemistry, because you are doing the master degree in that postgraduate degree for the chemistry. So in that subject, what is the application part of this mathematics and as well as biology both. So nowadays that as you know that it is that today that education system has been changed. Now we are in the topic of STEM: science, technology, engineering, and mathematics. So all are interrelated. Without anything else in between this, if you say that mathematics you can't do anything in case of your chemistry, as well as simultaneously biology you can do. You know that medical segment has been lots of things are related. Okay, so topic is why mathematics is important for chemistry. I have, if you come down to your that subject, you have gone through several things like your quantitative analysis, qualitative analysis, then your that average calculation of that speed of reactions, average speed of reactions, and then your what is that you can say the stoichiometric analysis. All of the there in several that mathematics applications are said there. So we have to understand basic things of derivatives. We have to understand calculus. We have to understand algebra. We have to understand functions. We have to understand. So these are the things. I'm an expert in case of math, that is your chemistry, but still we understand what type of mathematics and biology is there important in case of our subject. So the area we have to study for this is most important. So today we'll discuss that how the mathematics is important, what are the areas of mathematics are important. So where the application part is there in the mathematics. So let us understand these things first. I have to tell you something that is how it is important. So thing is that let's understand that how the in physical chemistry or that is in inorganic chemistry, organic chemistry, what is the how the mathematics is important. So let's understand that mathematics, if we just try to say, the mathematics is deeply intervened with chemistry. So that is lots of applications of mathematics there in that is chemistry field, providing the tools to describe, predict, and understand the chemical phenomenon. Here, how they are connected with the what type of area in chemistry that mathematics is connected. First is quantitative analysis. So what is quantitative analysis? When you calculate that if you are doing the titration strength of anything else, so you are calculating that the things, so that is your quantitative or salt analysis, whatever maybe, that is called as the quantitative analysis. In this segment, stoichiometric analysis is there, right? So chemistry relies on the math for the precise measurements. Moles, you know that you have learned that moles, concentrations, reaction yields, for example stoichiometric use in the algebraic equations to balance the equation, right? So that is most important thing, the algebraic balance of equation. That is most tricky methods how to means bigger or the larger, that is balancing of equations, how will do that one. So that is mathematical application part is there, right? That is all about the quantitative analysis. So in the quantitative analysis we use usually that what type of mathematics is used in this case. It will come down to the next scenario of mathematics, use of mathematics, the in the physical chemistry. In the physical chemistry, you know that this branch is heavily mathematical, full of mathematical concepts. So you will go to the any type of a calculation like your molality, normality, formality. So everywhere there is mathematical application. Even if that as I earlier I told you that average and that spontaneous, that what is the capacity of yielding of reactions, all everywhere, the chemical kinetics, the flow from the reactant to forward reaction or backward reaction, everywhere that application of mathematics is there. So this branch, if we say that physical chemistry, this branch is heavily mathematical concept, full of mathematical concepts like thermodynamics. Yes, exactly. That thing is that one is thermodynamics chapter is there, right? Chemical equilibrium is there. So in this segment, so heavy mathematical concept is mathematical things is applicable. So like that in the thermodynamics, it will say that enthalpy, entropy, in these segments that mathematical applications are there. And I just showed that chemical kinetics, rate of equations, like calculations is there, derivatives is there, right? So for instance, the rate of reaction is modulated with the differential equations. So like that rate of reaction, you have to find derivatives of facts, and derivation is application of a derivation is there. So that's why mathematics application is most important in these segments. So next, if you go to that another application part of this particular that is mathematics, so quantum chemistry. You know that quantum energy, that is structure part of quantum energy, nuclear chemistry. So all these things are related with the quantum means energy related things. So understanding atomic and molecular behavior of the requires advanced maths like linear algebra, differential equations, etc. So a Schneider equation is also there in the structure part. So that's why you have learned these things. So how the mathematics is the most important in case of that chemistry. If you go to the spectroscopy and data analysis, this is the modern technology. In higher study, you have all learned about this. If we say that application of calculation, derivatives, and all the things in the that field of chemistry, you have learned so many things. But now modern technology, now you are in MSc class, master degree class, postgraduate, in this spectroscopy is there. So in the spectroscopy, that is analysis or galvanometric analysis, or that is your what is mass fraction analysis. So that chromatography, all these analysis are there. And in these segments, you have your mathematics is most important part. The spectroscopy and the data analysis, that is NMR, IR, NMR, that report, you have to go through that one. That's why for that, so many mathematical transformation is there. And there is analytical statistical methods are there, and regression models are there. So these are the application parts of the that is mathematics in chemistry. If we come to the chemical modeling, so conceptual chemistry employs algorithm, so numerical methods, and all the things. So these are the application part in case of also that is chemical modeling of that particular in chemistry field. Mathematical application is there. And geometry, as you'll know, that geometry and symmetry, molecular shape, tetrahedral, octahedral, these are how, what is the bond angle, and all the things, that polarization, all the things we have to understand in this particular how the mathematics is applied in case of chemistry. So overall, I just give you an idea how that, what type of things we are going to that is read, what to understand. So by video lecture or audio lecture, whatever may be the things, so I'll share everything. So starting from the point, your chapter is saying, if you go to your syllabus, so past chapter is sets, and that is your unit 014. In that case, unit 1 is sets and graph functions. So how the sets and graph functions are there, and how it is implemented in this case of that is your chemistry, we have to understand first what is graph. All that. So for that, I can't in the modeling stage, but I can share you the video. So go through the video right now. Let's and understand the what is the graph and how the graph will be. That is that is what is the graph, and what is how the option of the graphs is there, how do you understand about the graph and all the, then we will go to the application part of this one. Okay, so just right now I'm sharing with the graph. Okay, this is the video of my one of our professor. So I'm sharing that introduction to graph first. So let's understand what is graph. You have to understand what is graph, then we can go through that particular things. So just a second, please.
We will study graphs from the algorithmic point of view. But
Yes.
we will do the graphs today as an introductory class just to introduce to you what are graphs, what are their applications, and how they are stored as data structures. And the next day onwards, we will start our manipulation of graphs. Graphs, as you know, is a structure which has got two major components. The first component that is there in a graph is called a set of vertices and a set of edges. So a graph G consists of two entities, a set of vertices and a set of edges. So a graph G consists of a set of vertices. So, so we have one or more vertices, and these are either called vertices or they are called nodes. And each node may have one or more labels. The labels of a node often identify the purpose for which this graph is to be used. So a node will be labeled, and we will see examples of how nodes are labeled. The second component of a graph, as we have seen, is called a set of edges or connections. An edge typically connects two vertices of a graph. So an edge usually defines a connection or a relationship between vertices or nodes. So in terms of a graph, we have two major entities of a graph. One is called the vertex or nodes. So there may be n nodes in a graph, and there may be m edges or m connections. And each connection is a combination of two vertices. For example, let us take this example which we have come to. Let us consider this example here. In this example, as you can see, we have got 9 vertices, 0, 1, 2, 3, 4, 5, 6, 7, and 8. And these vertices, typically in a graph, vertices are drawn using circles, and the node number or the node name is given inside the vertex. An edge is a connection between two vertices. For example, this edge is called the edge 08. Let me use a pen. So this edge in the vertex will be called the edge will be called the edge 08. So EI, which this is the edge EI, this edge EI is 08. Being an undirected graph, this edge can also be called 80. So it is just a relationship between two vertices. This graph is an undirected graph and contains 9 nodes, and how many vertices, how many edges? 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 3, 3, 6, 7, 8, 9. I'm sorry, there are 9 edges and 9 nodes in this graph. Consider this example. Consider this example. This is also a graph. While all of you may think that this second example, let us call it figure 2, let us think that you are looking at this and say that each of them are separate graphs. While each of them can be a separate graph, this itself is one single graph, which means that a graph is not necessarily connected completely. That means between every pair of nodes, we don't necessarily need to have a connection. These two, the figure 1 which we have here and the figure 2 which we have here, are called undirected graphs. That is what we said, that a graph can be undirected. On the other hand, a graph is said to be directed if the edge between the two nodes has got a direction. Consider this example of figure 3. This figure 3, as you can see, has got nodes or vertices A, B, C, D, E, F, and G. And it has got edges. Now each edge, as you can see, has got a direction. For example, the edge from A to D is the edge from A to D. Similarly, the edge from D to E, there is no edge from E to D. In an undirected graph, we can say that an undirected graph, an edge of an undirected graph, is equivalent to two edges of a directed graph. Again, here we see another important thing is this. That means what we have said here is that an edge can have one or more labels. The label of an edge depends on the application which is being used. In fact, even nodes can have labels, and we shall see them in terms of our examples where nodes can have labels, edges can have labels, and they can have multiple labels. Now we come to some special cases. Let us look at this example in figure 4. In figure 4, we see a special case of a graph having a self edge. It is called a self edge or a self loop. We also see that there are two edges from one node to another node. For example, from B to A, there are two edges in the same direction and there is one edge back. So these are what are called multigraphs, where a graph can have multiple edges from the same nodes. And we shall see examples of the same when we come to some problem cases where we will model problems in terms of graphs. In the most general case, till now we have seen a graph having an edge only between two vertices. But a graph can also have an edge between multiple vertices. Consider this example of figure 5 which I am showing here. Here you will see that we have got, this is vertex 1, this is vertex 2, this is vertex 3, this is vertex 5, this is vertex 6, and this is vertex 7, and this is vertex 4. So we have these 7 vertices. Now, and there is this, the red edge between vertex 2 and vertex 3 is a single edge. On the other hand, the edge between vertex 1, vertex 2 and vertex 3 is an edge that covers 3 vertices. Such edges are called hyper edges. So an edge could be, in general, an edge could be a binary relation, or an edge could be a relation between multiple vertices. Typically, an edge, in most problems that we see and encounter in practice, we model them as binary edges. But there are a large number of problems where we will model graphs in terms of hyperedges. So an edge, in the general definition, is a relationship between two vertices or more vertices, and therefore an edge is actually said to be having more than one vertex in the general case. So in the general case, an edge can be a relationship between more than one vertices. But for the problem that we will do in our course, we will only consider binary edges. There is a very strong relationship between set theory and the theory of graphs. And while that is out of the syllabus, but I think you should appreciate from the concept of hyperedges, from the concept of multi-edges, that graphs is a very, very powerful structure. We now move on to some applications in graphs. Graphs is such a wide topic that it is used almost in applications in every field that we see. For example, the most interesting and important application is in maps and routes. Let us consider this figure example. Let us consider this application figure 1. This application figure 1 is a map between cities. So the nodes of this graph are cities. So V is equal to the set of cities. On the other hand, E is equal to the set of direct flights between cities. So in this case, we have a graph GVE where V is the set of cities and E is the set of direct flights between cities. And typically, if it is a directed graph, then it will have a from to relationship where it will be the flight from this to that. Now, what could be the labels on the cities? The labels, obviously, on the cities, other than the city names, would contain many other pieces of information like the size of the airport, and then if we go into more details, all details about the airport. The most important information on the edge would be the time required for that particular flight from one city.
Now the thing is that if you connected these things with your chemistry, right? Graph and that is how the graph and sets of graphs is related to the chemistry. So suppose you have to take the one thing is carbon and carbon with that connected with how the carbon is connected with the different that is molecules. If carbon will the cities like that, V is the cities or V is the carbon, and E is the how it is connected with the different molecules, right? The molecules with different atoms. Suppose we will take that is carbon is related to the oxygen, carbon dioxide is there. Carbon is related to the oxygen, again carbon monoxide is there. Carbon is related to the oxygen, carbon suboxide is there. So many things are there. Carbon is the major, means it is the, you can say in the mathematical it is V, and also E is the different molecules which is connected with the oxygen, and different types of things is formed, that is carbon dioxide, carbon monoxide, and carbon suboxides. These are the three examples I gave you on the spot. So thing is that this is the application of a graph and sets up the graph in our chemistry, right? So okay, go through this video again and try to understand how it is linked with the that is chemistry. So that is the most important. Now you have to connect with the graph with the chemistry.
To another. Now we know that we have many airlines and each airline has its own timing. Therefore, the edge on that edge, other than just the timing, we could have the departure time and the arrival time as two labels on that edge. Similarly, we will see that this is a multi-graph where the
So thing is that now in this connection you have to say that same carbon when it's react with oxygen gives carbon dioxide, and carbon again react with that is again with oxygen, that is gives carbon monoxides. Carbon again react with oxygen, that is gives that is carbon suboxide. But what is the scenario, what is the sense, what how the things is happened? So it is controlled, uncontrolled, or sub-control, whatever the state, what is the primary that is the setups are there, how the atmospheric conditions will there, pressure atmospheric condition, I mean to say that is in chemistry atmospheric condition means it is STP or NTP, whatever the temperature that is pressure, how it is related with the, then carbon will react with the oxygen will give the carbon dioxide, then carbon with react with the oxygen will give what the, how it will happens, these things, this scenario is there. So that's why it is how the graph is most important with the that is sets of that is sets and graphs, how it is interlinked in the chemistry. So that is most important thing, you have to go through that.
whole airline itself, if we start now modeling and separating out the labels of the edges with which airline is flying, then on the edge between two vertices, we will have airline, we'll have flight number, we'll have expected time of departure and expected time of arrival. Later on, we could also have the cost and many other things on the labels. So the same thing will occur in terms of a road map. The same thing will occur in terms of a city map. The same thing will occur at various levels. Let's go to the next example. The next example is a layout plan. This layout plan shows a set of rectangles. physical layout. We could mention the locations as the. So in this graph, Alice likes Bob, Bob likes Alex. You have to fill in these words in order to of time that
If
is
you continue
required to
like that, so
execute
I'm
that
just
task.
going away from this one, this
Properties
video.
and algorithms
Okay,
are
now
simple.
graph representation. This is the
But
most
now
important
we
area of
come,
that one.
and each transition is an edge in the graph.
Okay.
There are other types of representations as well, but they are not popular and we will not discuss them. I will just show an example using this figure 1 to show how we develop an adjacency matrix and an adjacency list. For an adjacency matrix, we create a matrix or an array. Here there are 4 vertices and 4 edges. So this is an array where we have got so if since there is no edge between 1 and 2, between 1 and 1 there is no edge, between 2 and 2 there is no edge, between 3 and 3 there is no edge. So if there is no edge, we mark with a 0. If there is an edge, we mark with a 1. So between 1 and 2 there is no edge, and therefore there is no edge between 2 and 1. There is an edge between 1 and 3, and being an undirected graph, there is an edge between 3 and 1. There is an edge between 3 and 4, so there is an edge between 3 and 4, and therefore there is an edge between 4 and 3. And there is an edge between 2 and 4, and therefore there is an edge between 4 and 2. These are only the 4 edges that we have in this graph, and the rest of the edges are all 0. So this is an adjacency matrix representation. In case of weighted graphs, we shall see later what we do. But an adjacency matrix requires order n squared. If there are n nodes, then it requires order n squared space to store the edges in the graph. The maximum number of edges that can be there in the graph are NC2 for an undirected graph, and therefore you can choose any 2 pairs and there can be an edge between them. The other representation, especially which is useful when there are multiple vacant places in the graph, that means the number of edges are not as many, is called an adjacency list. For an adjacency list, we will show various ways to draw it. So we have an array of nodes. So this is node 1, this is node 2, this is node 3, this is node 4. And we have our pointers in terms of the data structures that we have. So what we can do is, we will now say 1 is connected to, I think I made a mistake, 1 was connected to 4 here, isn't it? 1 and 4 and 4 and 1 were connected as well. So I think we need to just correct this. So have we got all our edges? There are 2 from 1. There is 1 from 2. There are 2 from 3. And there is 3 from 4. So here, once we come back to this example, so here are our edges. So from 1, we have got an edge to 3 and an edge to 4. From 2, we have an edge to 4. From 3, we have an edge to 1 and an edge to 4. And from 4, we have an edge from 1, an edge to 2, and an edge to 3. We could also represent this in terms of an array, where in an array data structure, or a data structure where we, instead of this pointer, we could do it in a different way. We could have an array like this: 1, 2, 3, and 4. And then we could mention in the first row how many edges are there. That means there are 2 edges here, there is 1 edge here, there are 3 edges, 2 edges here, and there are 3 edges here. And after this, we could mention which edges they are. This would be 3, this would be 4, this would be 4, this would be 1, 4, and this would be 1, 2, and 3. There are various other ways in which you can represent, but an adjacency list representation maintains a list of edges to which it is connected, whereas an adjacency matrix representation, it maintains the full matrix of connectivity. Let us see what happens in the case of a directed graph. In the case of a directed graph, in an undirected graph, you had symmetric edges, and here it is not only a directed graph, there is a weight on the graph. So this graph, which has got 1, 2, 3, 4, 5, 6, 7, which are labeled A, B, C, D, E, F, G, would have 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, 7, marked as A, B, C, D, E, F, G. Again, A, B, C, D, E, F, G. And from 1, A to D, there is an edge. So there will be an edge of from A to D, and its cost, let us put in a different color so that it becomes clear. Its cost will be 3. Similarly, from D to F, we'll have 6. Similarly, from C to A, we'll have 3. And you can fill up this adjacency matrix where the values, instead of being 0 and 1, would be the weights associated with it. If there is no edge, you could either mark it as 0 if there is no weight 0, or you could mark it as -1 to indicate that there is no edge. Similarly here, the adjacency list would consist of labels A, B, C, D, E, F, G, and then from A you have got edges to B, so you would have to write B, and then you would have to write the value 5, which is the weight. You would have to write A to D, which is D, with the value 3, and so forth. And then, so for each one of them, for B, you would have to write to C. So for B, it would be one edge, one link, C having weight 5, and so on and so forth. And you could also implement it in the same way that I had mentioned earlier. So the adjacency list of a weighted or a labeled graph will have as many nodes. Other than the node label, it will have all the property labels which are associated with every edge. Now let us see what are the problems and the algorithms that we shall consider. The first problem that we shall consider is there a path from node X to node Y? For example, we may ask, is there a path from this node to this node? And we know that there is a path. On the other hand, we could ask whether there is a path from this node to this node. And we know that there is no path. So the reachability problem, which set of nodes are connected to each other, or the connected components problem. For example, in this graph, this is one connected component. This is a second connected component. This is a third connected component, and this alone node is a fourth connected component. In a directed graph, the connected component concept becomes a little different. We have also seen that trees are a special case of graphs. Trees are graphs whether they are directed or undirected, which have no cycles. A cycle is a path which goes through distinct edges and comes back to the original node. For example, in a graph like this is a cycle, this is a cycle. Suppose this is a graph A, B, C, D. Then this is a cycle, and this cycle will be both directions. Similarly, we have other cycles in the graph. This is a cycle, and so on and so forth, finding cycles. So a tree is a graph which has got no cycles. And if a tree is a graph which has got no cycles, then in a directed tree, we can order it in terms of orderings. And we have just discussed a little while ago about acyclic graphs. Costs and distances. As we just mentioned, a directed graph has got costs. And we may want to know, suppose this is a path road network graph. Suppose this graph of figure 1 is a road network graph. We may want to know what is the shortest cost path from A to G. And we can see that there are several paths from A to G. This is one path, A to D to G. There is another path from A to D to F to G. There is a third path from A to B to C to D to F to G, and so on and so forth. Our interest would be to find the shortest cost. On the other hand, this is an acyclic graph, whereas this graph has got cycles. For example, you can see that this graph has got a cycle like this. This graph, figure 2, has got no cycles. And if figure 2 has got no cycles, then we can order it in terms of the dependencies. For example, these two nodes have got no dependencies, and therefore they can be levelized to be put at level 0. This can be put, this is level 0, this is level 0. So these are the 4 nodes at level 0. This is at level 1. This is at level 2, because this is at level 1 and this depends on this. This is at level 2. This is at level 1. This is at level 1. This one has got 2 level 2 and 1 level 1 node depending. So this is level 3 and this is level 3. So we could order these nodes, and we shall see algorithms for ordering these nodes. So we have got various kinds of algorithms to solve for them, and we have got various problems by which we can work on them. Other 3 important problems, which we shall do at least 2 of them in this course. We just mentioned the shortest cost path problem. There's another problem called the spanning tree problem, and we shall discuss and define these kinds of problems which have got very widespread applications in computer science. And we shall examine these problems from the algorithmic point of view, and we shall see how the algorithms that we have studied in terms of the divide and conquer, the recursive definitions, the greedy algorithm, the dynamic programming method, the branch and bound methods, all of them are very widely used to solve some of these problems. So finally, to summarize, we come and summarize what we have. Graph G equal to VE is the data structure where V is a set of vertices, E is a set of edges. These could be undirected or directed, and they could have weights on the edges or labels at the nodes on the edges. They could be cycles or they could be acyclic. And there are several problems that we need to solve on these graphs.
So now we understand that is how the graph has the importance in this case. So that directed and undirected graphs at both are the things are there. So now the thing is that let's move to the how the that is undirected graphs are transversal in this case of that is the application in this case of mathematics, right? Just a second, I'm sharing the screen. Okay, now I'm going to share you the screen. That is how the what is the importance of an undirected graph in the segment of it is mathematics. So let's understand this one.
Hello everyone, welcome to our second lecture on graphs. Hello everyone, welcome to our second lecture on graphs. In the first lecture, we gave an introduction to graphs, mentioned their application. There are 10 edges 0 to 1, 0 to 8, 0 to 3, 1 to 7, 2 to 3, 2 to 5, 2 to 7, 3 to 4, 4 to 8, and 5 to 6. So, based on these, we know that the number of vertices in the graph is 9 and the number of edges in this graph is 10. And these edges have no labels. In general, we will use a very important function called the successor function. The successor function, given a node I, the successor function gives the set of nodes to which I is connected. For example, if I ask for the successor of node 2, then I will get node 3, node 5, and node 7. If I ask for successor of node 1, I will get node 0 and node 7. Similarly, if I ask for successor of node 4, I will get node 3 and node 8. This successor function is a function that we will use consistently throughout our programs and our algorithms. The second part is about directed graphs, undirected graphs which are weighted. That means in the figure 2, as you can see, that these edges have weights on these edges. As we have seen in the previous day, these weights can be various labels. For example, in a city map, these nodes can be points in a city, and the weight on those edges can be the distance between those points. Similarly, there could be other variables which assign the label or the weight to this undirected edge in a weighted undirected graph. We now come to the important problems that we want to solve in an undirected graph. The first problem is the reachability problem. The reachability problem is as follows. Given two nodes of a graph, we would like to know whether there is a path between them. So what is a path? A path is the sequence of edges between nodes from one vertex to another vertex. For example, if I want to know what is the path between 0 and 8, then there is a direct path between 0 and 8. On the other hand, if I want to know a path between 0 and 5, then here is a path between 0 and 5. There is another path between 0 and 5. There is another path between 0 and 5. And there is a third path between 0 and 5. Therefore, a path is a sequence of nodes which contain edges from one node to another. So it's a sequence of edges between nodes. We also need to remember that there is a slight difference between a path and a walk. In a path, typically, no nodes are duplicated. whereas in a walk, a node may be duplicated. A cycle. A cycle is a path where you start from one node and return back to that same node. For example, this is a cycle. That means you start from 0, go to 8, go to 4, go to 3, and go back to 0. So finally, and a graph which has got no cycles is known as a tree. The other important problem is called the connected components problem. Let us look at this figure here. This figure here, you will see that there is no path from this node to this node. Since there is no path from this node to this node, therefore this node is not connected by a path in this graph. So all nodes which are connected by a path form a connected component. And in this graph, we will see what are our connected components. If we notice, we will see that this part is one connected component. This part is a second connected component. This part is a third connected component, and this node alone is a fourth connected component. So how do we find connected components in our graph? Then there are more complex problems which are called the bi-connected component, the spanning tree, the shortest path, the maximum flow, the vertex cover, the edge cover, the traveling salesman problem. For example, if we go to figure 2, we will see that here is the issue of a shortest cost path. Whereas in figure 1, if we want to know the shortest length path from 0 to 5, then we know that this path is of length 1, 2, 3 edges, whereas this path is of length 4 edges. So we would like to find the shortest length path. On the other hand, in a weighted graph, the shortest length path need not necessarily be the shortest cost path if we consider the sum of the edge costs to be the cost of the path. So finding the shortest cost path is an important problem. For example, the vertex cover problem is a problem by which we try to find the minimum number of vertices of a graph that cover all the edges. The edge cover problem is just the reverse, where we try to find the minimum number of edges in a graph that cover all the vertices. So a graph has got many problems, and we will now see how we will be able to address those problems by some simple traversal algorithms. The basic traversal algorithm in a graph is called the depth first search algorithm. It is a recursive algorithm which has a global variable called visited. The variable visited, as indicated in this variable, this variable visited indicates if a node is visited by the search algorithm or not, and it is initialized to 0. As mentioned earlier, we will also use the successor function, which is the set of all nodes to which the node is connected. So how does this algorithm go? This algorithm works as follows. This algorithm is called at any node I, and let us say it is called at a node. The first step we say is we mark visited equal to 1. And then for every node j, which is a successor node, we check if it is not visited. If it is visited, we don't do anything. If it is not visited, we recursively call this DFS by DFSG. So now let us see how the algorithm operates, and let us find out how the algorithm runs. So initially, we now have the algorithm where, let us say we call this algorithm at node 0. And let us say all nodes are initially marked visited equal to 0. And if we call this at node 0, then let us try to find out the sequence in which the depth first search traversal goes on. So firstly, by the algorithm, this node with node 0 will be marked visited equal to 1. Whenever a node is marked visited equal to 1, I mark it by a red circle here. And I also number it. I number this node as the first node visited. Then what are the successors of 0? 1, 3 and 8. So the algorithm will now check whether visited 1. So it will have to, from 1, it will now call, from 0, it will now call 1, 3 and 8, but recursive. So now it will go to node 1. Node 1 we know visited is 0. So it will, since node 1 visited is 0, it will visit node 1. So it will go to node 1 and visit node 1. So it will go into node 1 and say visited node 1 equal to 1. So this node is marked visited, and let us say that this is the second node visited by the algorithm. Now what are the successors of 1? The successors of 1 are 0 and 7. But 0 is already visited. Therefore 0 need not go. So the algorithm will now go to 7. So the algorithm from 0 went into 1, and now from 1 there are two successors. 1 has got two successors, 0 and 7. But since for 0 visited is already 1, it will go to 7. So now it will go to 7 and mark 7 to be visited. This is the third node visited. Once 7 is visited, then what will happen is, it will find what are the successors of 7. The successors of 7 are node 1 and node 3. So what it will now do is that since node 1 is already visited, because this checks whether if visited is equal to 0 only, then does it call. So therefore, it will not call DFS node 1 again, and from 7, it will call node 2. Once it calls node 2, it will mark node 2 as visited, and node 2 will be the fourth node to be visited by the algorithm. Now node 2 has got three successors, 3, 5 and 7. So node 2 has got successors 3, 5 and 7. But since 7 is already visited, it will not visit node 7. So it will now go to node 3, and node 3 will be the fifth node to be visited. So node 3 is the fifth node to be visited here, and the algorithm, after going to node 3, will mark it and look for the successors of node 3. Who are the successors of node 3? Node 3 has successor 0, node 3 has successor 2, node 3 has successor 4, and node 3 has successor 8. But two of these successors are already visited. So from node 3, we will now go to node 4 only. Sorry, node 8 is not a successor. It had got successors 0, 2 and 4. So it will go to node 4. And node 4 will now be marked visited. It will be the sixth node to be visited. And from node 4, it has got two successors, 3 and 8, of which 3 is already visited. So from node 4, it will go to node 8. So these are all the nodes that are visited till now. It has now gone to node 8. After it has gone to node 8 is the seventh node to be visited, and it is marked visited. After node 8 is visited, then it goes back, because all the other successors of node 8 are already visited. Therefore, the algorithm will now backtrack and go back. So from node 8, it will go back to node 4. And in node 4, so from node 8, it will go back to node 4. In node 4, once it goes back to node 4, no other successor is left, so it will backtrack back to from where the DFS was called. It will go to node 3. Now node 3 has got all visited, so it will now backtrack to node 2. In node 2, we still have node 5 which is to be visited. So now by the algorithm, DFS will again call node 5, and node 5 will be my 8th node to be visited, and node 5 will be visited. Now node 5 has got two successors, node 2 and node 6. Now node 2 is already visited, so node 6 will be visited. So it will now go to node 6, and node 6 will be visited, and node 6 will be the 9th node to be visited. After node 6 is visited, node 6 has no non-visited successor, so it will backtrack. Now it will start backtracking, and it will backtrack from node 6 to node 5. From node 5 it will backtrack to node 2. From node 2 all successors are visited, it will backtrack to node 7. From node 7 it will backtrack to node 1. From node 1, as we can see, all successors are visited, it will backtrack to node 0. From node 0 it will try to come to node 3, but node 3 is already visited. So it will not call node 3. It will go and try to visit node 8. So node 8 is also visited. So based on this, we have done a traversal of this, and the sequence of traversal is 1, 0, 1, 7, 2, 3, 4, 8, 5, and 6. So this is how the depth first traversal works. If we reorder the successor function, the traversal will be different. I will suggest that you reorder the successor function, or I will make a suggestion for you to try the following as an exercise. Try by starting at node 2. Let us say, try by starting at node 3. If you start at node 3, then what will be the sequence? If you start at node 2, what will be the sequence? And so on and so forth. So this is the basic depth first traversal algorithm. It is a foundational algorithm, and this algorithm has applications in many, many cases, and we will come to them systematically. We now look at the basic traversal algorithm on another example. Suppose this is an example of a graph, as we have seen, that if we start the traversal of DFS from here, then we will visit this node first, this node second, this node third, and the algorithm will terminate. On the other hand, if we start from here, somewhere in this part, then the algorithm will only look at these and terminate. So I will request you to find out that, so for example, if I call it at this node has got no successor. Therefore, the algorithm will just mark this node visited and terminate. Which means that the basic traversal algorithm need not complete the full graph if we use only this portion of the code and call it on a single node. Now, how do we traverse the full graph? All we need to now do is traverse this graph by calling it by a function from the beginning, and then using this we can also do some very important techniques which we can see now. On the other hand, if the graph was a tree and it is a fully connected tree, not a forest, then if you start, let us say we start from here, then this will be visited first, this will be visited second, maybe this or this will be visited third, depending on the ordering. Say this is visited third, this is visited fourth, this will be visited fifth, this will be visited sixth, this will be visited seventh, this will be come back to be visited eighth, this will be visited ninth, this will come back here, this will be the 10th node to be visited, this will be the 11th node to be visited, this will be the 12th node to be visited, then it will come back here and this will be the 13th node. So this is how you traverse a graph or a tree. Wherever you start from, the sequence of visits will be different. But for if the graph is connected, then all the nodes in this graph will be visited. That is how the algorithm works. Now we come to the application of this algorithm. This algorithm can be used for various interesting purposes. For example, the first thing that we can do is to detect whether there is a cycle in the graph. For example, in this node, we know that there is a cycle. How do we detect that there is a cycle? What is the condition? The easiest condition for us to detect that there is a cycle is that if the node is already visited. For example, if we started here, this was 1, then we came here, this was 2, then we came here, this was 3, then we came here, this was 4, then we came here, this was 5, and then we come back to 0, and we know that there is a cycle like this. So it would be easy for us to say and write a piece of code here saying that if we could try and write a piece of code here, if j if j is visited, which means if, let me erase this cycle. We could write if and mark cycle. But there is a slight catch here, because if we go from 0 to 1, then a successor of 1 is also 0. So we also have to check that if j is visited, but j is not a direct connection with I. So all if visited j equal to 1, and we have to see that there is no edge between node and between this j, that j, when we say this, when we are checking for each j, which is a successor of this node, we also have to check whether this again does not go back to a back edge of this node, which means that I will check for cycles to check whether a node is visited, except for those pieces of the code of the node which is back its parent, or which is also a direct connection of this node. I will leave the detection of cycle part to you. This is not the code detection, cycle detection code, and I am leaving it as a small assignment for you to do, to include how we will detect cycles in a. Similarly, here, if we start from this node, this is the first node visited, this is the second node visited. Now, this has this as a successor as well as this as a successor. For this successor, when I go, this is a visited, but this does not detect a cycle because this is a direct connection. So, I will detect the cycle only if the path through which I have come is not the same as the path through which I am going to go back. So this will be a cycle, whereas this is not a cycle. So I leave it to you to write this piece of code to find out how a cycle is to be detected. The third is that how do I find the path, any one path between I and j? That means while I am visiting, how do I find a path between I and j? Now, in order to do this, we define two kinds of edges. One is called a tree edge and one is called a back edge. And we maintain what are called parent links. So, when I am searching from this node to this node, that means when I am going from a visited node to a not a visited node, then that edge is a tree edge. So, this will be a tree edge. This will be a tree edge, this will be a tree edge, this will be a tree edge. Whereas once I go back here, This will be a back edge. So I'm marking the back edges by red and the tree edges by blue. Then again I will come back and mark from 3 I will go to 4, which is a tree edge. From 4 I will go to 8, which is a tree edge. From 8 I will go back to 0, which is a back edge. Then I will come back here and then again I will get this as a tree edge. Then I will get this as a tree edge. This completes basically my whole search. So I have got 1, 2, so I could mark these as my tree edges. And if I remove the back edges, then this forms a tree, as you can see, without any cycles. And the back edges end up in cycles. So what we could do is, for every node, we could mark a parent node P of a node I. For example, the parent node of 1, P1, is 0. Similarly, P7 is 1. Similarly, P2 is 7. Similarly, P3 is 2. Similarly, P4 is 3. P8 is 4. P5 is 2. And P6 is 5. Now, from the parent nodes that we have, if I have Pi, then once I have a path from any node to any node, then through this depth first search, then by just tracing back through the parent nodes, I can determine the path from the original. So pathfinding can be done, pathfinding can be done by tracing back from the parent node. I leave it to you to write pieces of code here and pieces of code here and pieces of code here, all these places. I leave it to you to update these pieces of code so that you can now find out, modify DFS search to really find out a path between two nodes by maintaining this parent node structure. As we said before, that a graph need not be fully connected. So an important problem for us to solve is to find out what are the connected components of a graph. So given an undirected graph, our objective is to find the connected components. We know that there are four connected components in the, there are 1, 2, 3, 4 connected components in this graph. So what we do is, in addition to the visited array, which we already had, we declare a new global data, which is called the component I. And like visited is assigned 0, all nodes have a component number, and this component number is assigned 0. We keep a basic count to 0 to initialize the global component count. And this is how the algorithm works. The original DFS algorithm does the same thing. So the first thing, I'll come to the overall main algorithm, but first let me discuss the algorithm, which is the modification of our DFS search at a node. So this part is same, it marks visited equal to 1. And then it does an important thing that we just used the component function. So what it does is, it assigns component equal to count. And then for each successor which is not yet visited, it recursively calls. So the only addition is that this component of a node is assigned the value count. Now what happens in the main program? In the main program, we know that count is globally initialized to 0. So what it now does is for each node k, as we saw in DFS, it may terminate by not visiting all nodes. So we want to ensure that it visits all nodes. So that is why before calling this, and once it comes out of this, we have a global loop by which we say for every node k, if visited k is not equal to 0, we increment count and call the recursive algorithm. Sorry, this recursive algorithm name will be dfcomp, because this is dfcomp. This is dfcomp. So now what happens is that let us see how it works. Let us see how this ensures that we have the component numbers down. So let us work on this example that we have. So suppose we start with this node, node number 1. So node number 1 is marked visited, and so for each node k, so let us start with node 1. Visited k is 0, so count is 1, and we call df count. So now count is 1. So now we are going to mark two values. One is whether it is visited by a circle, and then whether the count value, the component value, we are going to give the number. So here component value will be 1. Then let us say this node will be visited. Component value will be 1 because it goes on, the component value does not increase. Then let us say this node is visited. Sorry, this component value is still 1. Let me erase this. So this component value is 1. Then it visits. So after it comes here, it visits this node. Its component value is 1. Then it comes back and visits this node. Its component value is 1. It visits this node. Its component value is 1. It visits this node. Its component value is 1. It visits this node. Its component value is 1. And the algorithm will complete. This part will come out. And it will go back because there is no other connection from here. And all these are the same component, connected component, and all have been labeled 1. Now it will go to node 2 is visited, 3 is visited, and so on and so forth, till it comes to node 9, which is this node. Node 9 is not visited. So it will check node 9 is not visited. Now count will be incremented by 1. Count will become 2 and it will call node 9. So this node 9 will be visited. This will be incremented by 2. This will be visited. This will be incremented by 2. Next, it will complete because there is no other node to be connected to this. So it will come out and go back here. The next not visited node is node 11. So it will go to node 11, but before that it will increment count to 3. So node 11 will be visited, count will be 3. Then the next node will be visited, count will be 3. Then the next node will be visited, count will be 3. Again it will come back, and then it will call node 14, but before that it will increment count to 4. So by this algorithm, as you can see, we have identified 4 connected components. And the count value that we have is the component number. Now let us look quickly at the complexity of these algorithms. The algorithms are very simple. The algorithms visit every node exactly once, because if it is visited, it is not checked, and therefore it traverses every edge exactly once. Therefore, the complexity of these algorithms are of the order of B plus B. So these are called linear time algorithms and are very effective in rapidly detecting properties that we have just seen, whether there is a path, whether there is a cycle, whether there are connected components. Now we could make this more and more complicated and interesting. For example, at the beginning of every node, we could determine that we have already done a numbering which we showed. So we could do a numbering here to show the sequence of nodes visited. We could also put a timestamp T1 here and a timestamp T2 here to indicate when it enters a particular loop, when it enters a particular node, and when it backtracks from that node. For example, we could find out when it has entered this node, and from once it enters this node, from here it will come to this node, then it will come to this node, then it will come to this node, then it will come back here, then again it will go to this successor, do this whole part, come back. So there is a timestamp of entering this, there is a timestamp of doing all this and going back to this. So these two timestamps also give various properties of the graph, which we shall see. I will request you to start reading about depth first numbering and entry exit timestamps. And it is used for various other methods, algorithms, of which one very popular algorithm is called finding the sorry, bi-connected components. We will do these numbering and other things in more details later on, but I'm just giving you an idea, and I would request you to update this piece of algorithm piece of code to look at bi-connected components. We could also do breadth first search. So how does breadth first search work? Whereas depth first search is a recursive algorithm using a stack, breadth first search is an algorithm which uses a queue to maintain the sequence of nodes visited. So what it does is, it has a global queue, queue which is initially empty, and you call it with BFS any node k. It marks k equal to visited and puts k in the queue. This is the start node from which the breadth first search starts. After that, it performs the following. It checks whether the queue is empty or not. It removes the first element of the queue, and for this element of the queue, it checks whether it is visited or not. If it is visited, it does nothing. If it is not visited, then it marks it to be visited, and for each k in successor j, it puts it into the queue. So if this node which has been removed has already been visited, it does nothing. Otherwise, it marks it to be visited and enqueues it. There are various other ways in which you can do it. This is one way in which you can do that. So let us see how the algorithm proceeds. Let us say we start from 0. So then the algorithm proceeds like this. So initially q is node 0 by this method, by this part. Then 0 is removed because all visited are marked initialized to 0. 0 is removed and 0 is marked visited. This is the first node that is removed. Then what happens? Each successor. Who are the successors? 1, 3, and 8. So this is removed from the queue, and then the queue becomes 1, 3, and 8. And then the algorithm again goes back here, because this is not a recursive algorithm. Among this, Again it goes back, Q is not empty, so it dequeues this Q. Which element gets removed? This element gets removed. So it is marked visited, and this is the second element. Once this is removed, then what is put back into the queue? 0, 7, and 2. Because all successors are put back into the queue. Here, what we could also do, for each k in successor j, we could also say if visited k not, sorry, if visited k is equal to 0, then only we could have enqueued q. If we did this, then we would not enqueue 0, we would enqueue 7 only. So the next step, the queue would become 3, 8, and 7. Because it's a queue, it will enter at the end of this. So now this is visited. Now what is removed? Something from the beginning of the queue. So the next node that is going to be removed is going to be this node. Once this node is removed, which successors are going to be put? 0 will not be put, 2 will be put, and 4 will be put. So the queue now becomes 8, 7, 2, and 4. Again, the whole thing proceeds. From here, we remove the first element of the queue. So the node that is going to be next removed is 8. So the sequence of node removals will now be 8. And once 8 is removed, only 4 is already added to the queue. So 4 is added to the queue, 0 is in the queue, all are visited. So new node is added. So we have 7, 2, and 4. After this, 7 is removed. So 7 is the fifth node to be removed. After 7 is removed, 2 is already in the queue. So no new node is added to the queue. And the queue now becomes 2 and 4. This is how the queue works. This is step 1, this is step 2, this is step 3, 4, 5, 6. This is how it is done. Next, in step 7, node number 2 is removed. It is the sixth node to be removed. Once 2 is removed, 5 is added to the queue, and therefore we have 4 and 5 in the queue. After this, node 4 is the seventh node to be removed. In the next step, we have the queue only having 5. After 5 is removed, 5 is the eighth node to be removed. In the next step, the queue has got node 6. And then 6 is the ninth node to be removed. And therefore, in this step, Q becomes null. And once Q becomes null, the algorithm terminates. So as you can see, depth first search has a particular ordering which goes deep down. Breadth first search has an ordering similar to this. It goes like this. It goes breadth first. And so on and so on. So a frontier is created in breadth first search, whereas in depth first search, this method moves in a different direction. Both of them are of the same order of complexity of order V plus E, but both of them, in terms of their numbering, in terms of their properties, have got different properties. For example, we could maintain the parental links, and while in depth first search, the first path that you get from a node to another node is not necessarily the shortest path. If you use breadth first search, the first path that you get is the shortest path in an unweighted graph. Now let us come to a weighted graph. If a graph has got weights, then how do I find the shortest path? If I use pure breadth first search, then the shortest path is not necessarily obtained because a path may be of length 2 but cost 25, whereas a path may be of length 3 but cost 5. Therefore, just enqueuing and dequeuing will not work. I am just giving an idea today. We will discuss this in more details when we discuss finding the shortest path. But just to give you an idea, what we need to do is order the queue in order of the costs of the path of a node that has been obtained and update the cost of the path whenever you find a new. I have written down this algorithm. I will request all of you to study this algorithm, go through it in details, and then it will be easier for us to discuss this algorithm. This sort of an algorithm which we are going to do to find the shortest path in a weighted undirected graph or in a directed graph. For example, a directed graph can be considered to be an undirected.
Okay, so in this video we have seen that how this is your direct undirected graph is working on. Right now we'll go to the directed graph. So I'm just sharing with the video. Go through it.
Graphs. And now we begin our lecture on the traversal of directed graphs. Directed graphs, as you may know, have got edges and vertices like in ordinary graphs, but the edges are directed. That means the edge from one vertex is to another vertex. Unlike in undirected graphs, where the edges connected the two vertices, this here, the edges are an ordered pair of vertices. So the edges earlier, the edges are now directed edges, and therefore as a pair, it's an ordered pair. In any case, the successor function, which we had mentioned earlier, remains the same. This is an example of a directed graph. Here we have 10 vertices A, B, C, D, E, F, G, H, I, J, K. And as you can see, from A to B, the edge has got a direction. So this is a directed edge from A to B. All edges in a directed graph are directed from one direction to another. If there are edges between both of them, then there will be an edge from B to F and an edge from F to B. In general, an undirected graph can be represented by a directed graph by including edges in both directions. Directed graphs have also a special category. Whereas in undirected graphs, if there were no cycles, then they would form a tree. But in a directed graph, even if there are no cycles, they need not form a tree. Take this example. This is an example of scheduling where an expression is computed. For example, A and B are added here by this addition computation. The result is multiplied with C, and again here this result is added to E, and therefore both of them are added again together to get the final expression. As you can see that there is two edges coming into this plus node. However, there are no directed cycles. If this was an undirected graph, that is, this edge did not have a direction, then if this edge did not have a direction, then we would get a cycle. However, in an undirected graph, there are no cycles. Finally, a directed graph could also be a weighted graph. So there could be weights on the edges. So in terms of our definitions, we can have a normal directed graph as in figure 1. We can have a directed acyclic graph or DAG. So these are called DAGs. Directed acyclic graphs. They are graphs which contain no directed cycles, and there could be weighted graphs, or there could also be weighted directed acyclic graphs in such cases. We will study all these cases together and look at the traversals of all these cases. As usual, we use our basic traversal technique, which is the recursive technique, and as we have been doing recursive algorithms throughout this course, we will use the same recursive technique that we have seen in the undirected case. Here again we maintain, as we have shown earlier, we maintain a visited array which indicates whether a node is visited, and it is initialized to 0. As we had mentioned in the previous day, we maintain a parent pointer. So this is a parent of a node in the search. How is a parent defined? A parent is defined as follows. A parent, as we had mentioned in the previous day as well, a parent is defined a node parent of I is equal to j if there is a traversal from I to j and j was not visited earlier. That means in the algorithm, whenever what we are doing in the algorithm is as follows. As soon as we enter DFS of a node, we mark the node visited. This was before. Then for each vertex j, which is a successor, if it was not already visited, we were visiting it. But now we are adding this part to it. We are saying that we will mark the parent of j as node, which means the parent of I is j. If there is a traversal, this should be, let me just change it. If there is a traversal from so the parent of I is j if there is a traversal from j to I and I was not visited earlier. This is our case. So in our case, if the node j was not visited, then the parent of j is marked node and you do depth first search. So this being the case, let us now look at how we are going to do depth first search on this example and how that proceeds. So how are we going to do? Let us say we start from this node. If we start from this node, then we mark A visited as per the algorithm. Let us keep the algorithm at our side. We mark A visited. So whenever a node is marked red, it is marked visited. As soon as it is marked visited, there is only one directed successor of A, that is B. And therefore, we go here and we mark B visited. But before entering, because B was not visited, we mark parent of B to be A. So this is the parent of B. I am marking the parents at the node. So the parent of B is marked as A. and we have moved from B to A. Let's make a little neater. So parent of B is marked A and we do DFS of B. As soon as we go into DFS of B, then we mark B as visited. And then there are how many successors? One is C and one is F. So we go to C, and first thing that we do is we mark the parent of, so parent of A is null. Parent of C is B, and we recurse and do DFS of C. Once we have done DFS of C, then we have these two children, three children of C, B, C. One is A, but A is already visited. Then we have to go to E. We go to E and we mark the parent of E as C. Then from E, we can go to H. We mark H and we mark C, E as the parent of H. Then we come back from here. So we are going to backtrack from E back to, from H back to E. And then there is, we go to K and we mark E as the parent of K. From K, we move to J and we mark K as the parent of J. From J, we go to E, but E is already visited. So we backtrack up to here and then we come back to D and we mark D as visited. And before doing that, before entering D as visited, we mark the parent of D as E. From D, we go to G. We mark G as the parent of D as the parent of G. From here, we go to I and we mark G as the parent of I. And then we go to D, but D is already visited. So we backtrack all the way from here. This edge is in this direction, so we cannot go this side. We backtrack from all the way to here. We back up here. We back up here. And then we had left to go to F. So now we go to F. And after we go to F, we mark B as visited. B as the parent of F. From F, so this way we have covered all the nodes. We have marked all the parents. And from the parental structure, we can find out all the nodes, all the paths from the nodes right up to the start of the search. So this is how we do a depth first search of this traversal tree. Let's go to a slightly different scenario. Let us say instead of starting at A, instead of starting the depth first search at A, we start the depth first search at D. If we start the depth first search at D, because we have not mentioned where we will start the depth first search, we can start the depth first search from any place and let us assume we'll start it at D. If we start it at D, then D is marked visited, parent of D is null. Then we go to G, G is marked visited, parent of G is D. From G we go to I and parent of I is G. And this is visited. This goes back and the search terminates here. As you can see from this DFS, unlike in an undirected tree where the edge is in both directions, if there was any connection, you would have continued the search in a graph that is connected undirectionally. But in a directed graph, even if there are many edges and all the edges and the graph looks connected, it may not be connected in direction. So we started from A and we reached all the nodes. We started from D, we reached only these three nodes. So we, as we have done in the previous undirected case, we have to write an outer loop. In an outer loop, we have to write for each node I, if visited I equal to 0, then DFS. So this is an outer loop. So after completing this, we'll call it on another loop. Let us say we call it at E. If we call it at E, then E will have null. From E we will go to H. H will have parent E. From H we will come back here, go to K. It will have parent E. From K we will go to J. J will have parent K. From this we will come back. From here we will go to D. And D is already visited. Now we will notice that there are two unique kinds of edges. One edge, which was an edge which goes to a node which is not visited before, and we mark them as a tree edge. Whereas if a node goes to another edge which is already visited before, then we mark it as a different kind of an edge, and we will say that it is a cross edge. And we will define cross edges, tree edges, back edges, and several kinds of edges in the next class. But this also, if you see that this DFS terminates this way, so you will call it in the outer loop again. This outer loop will be written in the main program. This outer loop will be written in the main program. And then maybe we will call it here. If we call it from B, then B will have null. From B, we will go to C. C will have parent B. From here, we will go to this node, which is already visited. Then we will go to A. A will have parent C. From here, we will go back. From here, we will go to F. And F will have parent B. And now we complete all the nodes, and we have done a depth first traversal. So you can notice that in this case, the depth first traversal required us to go through three phases. In the first phase, we did this one. In the second phase, we did these. And in the third phase, we did these. And all of them, if you start from A, everybody is connected. But if you started from somewhere else, they are not connected. So path finding, cycle finding, all of these have a slightly different ramification when we go to a directed graph. Now, to analyze directed graphs a little better, we start doing a little more numbering, or we start tracing the whole process in a slightly different manner. So we now add a few more markers into the search process to identify exactly how a node is exiting and a node is entering. Whenever a node is being entered, we mark it by a timestamp. When a node is being exited, we mark it by a timestamp. And therefore, in order to do that, we add a few more variables, which I am going to describe in more detail now. We already had our visited variable. We already had our parent variable. We introduced two more variables here. One is called entry I, which indicates the sequence in which a node is entered, and exit I, which indicates the time sequence in which a node is exited. And we maintain a number which is the global timestamp. So this is a global timestamp. So what we do in the search now is, as soon as we enter, we increment the global timestamp and timestamp the entry point of a node. Then we complete the search as usual as before. And then after seeing all the children, again before exiting, we increment the timestamp and then ensure that we are putting an exit timestamp. So just adding these two, we are now gaining more information about how we are doing the search. We will now look at this on this example. So what we will do is we will look at this example and show how we are entering and exiting nodes. So let us say we start from this point. So we enter this node, mark it visited. Num, which was initialized to 0, is now becoming 1, and therefore the entry node is marked 1. From 1, we go to B. We enter this node and mark the entry point as 2. From B, we go to C. We enter this node and we mark its entry timestamp as 3. From C, we go to E. We enter this node and we mark its entry timestamp as 4. From E, we go to H. We enter this node and mark its entry time as 5. Now look at H. H has no other successor. Therefore, we are now exiting from H here in this part of the code. Since we are exiting from H in this part of the code, we will do an exit numbering of H. The num will be increased by 1 and the exit number of H is 6. Then we come back to node E, and node E is not yet complete. Therefore, we will go from node E to node K. And from node K, we will mark its entry number as 7. From K, we go to J, mark its entry number as 8. Now J this is already visited. So we are going to return from J and we will mark its exit number now as 9. Once we have marked exit number as 9, we go back to K. And from K we are going to exit, so we will mark its exit number as 10. Now we go back to E, but E is not yet complete. E needs to go to D. So since E goes to D, therefore we are now entering D. And D's entry number is 11. From D we go to G. G's entry number is 12. From G we go to I. I's entry number is 13. I need not go to D because D is already visited. So I exits. Because I exits, therefore the exit number of I becomes 14. We go back to G. Now G exits back. Therefore the exit number of G is 15. Once we have gone to the exit number of G, we go back to D. And D has seen all its children. So D exits and its exit number is 16. Now we go back to E and E has completed. Therefore E goes and exits. The E's exit number is 17. From E I go back to C and C has completed. Therefore C, because C has got this child, and this child, all are visited. So C goes back and its exit number is 18. Once its exit number is 18, it goes back to B, but B still needs to see F. So now F becomes visited. And once F is visited, for F, we have its entry number 19. Now F's child D is already visited, so we return to D, and therefore it has its exit number as 20. From D we go back to B. Now B has seen all its children. It exits and its exit number is 21. It goes back to A and its exit number is 22. So from this we have now seen, we have got the entry and exit numbers of nodes. We also now see from the sequence of these nodes, we can now identify various kinds of edges. We can identify edges which are of a variety of kinds, and based on this entry exit numbering, we will be able to see very interesting properties. We will notice that from the entry and exit numbering, for any edge UV, the entry of U and the exit of U The entry of U, it enters a node U, it enters a node V, it exits a node V. This from this node A, so let's use a different color. From 1 to 2 is, let us look at this scenario when we came from D to G to I and came back. Now, obviously, this edge is a tree edge because this is 1116, this is 1215. This is a tree edge. Now look at this edge. In this edge, this one lies between these two, whereas in this one lies between 1215 lies between 1116. Whereas here from this side, if we go, 1314 lies between 1116. Therefore, this edge is a back edge. And a back edge typically tries to identify whether there is a cycle in the node. So this node, this is a very interesting type of a node, and this node is called a back edge. This
Okay, so this is all about the directed graphs, and tomorrow that is we will go for that your calculus and differential equations, vectors. So thank you very much for your time.